All right, here we go. We're going to do a little linear programming today. So the first is just a little warm-up problem you might want to try on your own, and this is the answer you need to get. Okay? What this is all about is taking systems of inequalities to a new level, and we are going to start applying it to real-world application known as linear programming. Okay, so a couple of definitions, things to talk about first. Optimization. That's finding your maximum and minimum values. Now we're going to be applying that to like business type situations or store type situations. You'll get it after we do a few examples. And then one of the types of optimization is linear programming, and it's done by an objective function which is subject to a system of inequalities called constraints. And then we graph them, and our final answer is known as our feasible region. Now, a way to do linear programming, the first thing you have to do is have perfect graphs. The second thing you have to do is find the intersections of those perfect inequalities. And then the third thing you need to do is substitute the intersection points back into the objective function to find your minimum and your maximum. So there's two types of feasible regions you could have. You can have a bounded one, and that's going to give you a maximum and a minimum. And then you can have an unbounded one, which is only going to give you one or the other. You will not have both a max and a min with a unbounded feasible region. So, to understand all of this better, we are going to go do a couple examples. And as soon as you see those examples, it will make a lot more sense to you. Okay? So, here's our example. We have an objective function of c is equal to 2x plus 4y. And our constraints, x has to be less than or equal to 3. The sum of x and y has to be greater than or equal to 3. And then 2x minus 3y has to be greater than or equal to negative 9. So the first thing you have to do is perfect graphs. So we have x is less than or equal to 3. Now I'm going to shade these after I graph these lines. Okay, so this one, x is less than or equal to 3, so that one's going to shade to the left for me. You can do it any way you want. Then the next one is x plus y is greater than or equal to 3. You can do that using intercepts, or if you prefer, you can say y is greater than or equal to negative x plus 3. Either way you want, I'm fine with it. So perfect graphs, you might want to do a couple of dots in both directions so you make sure that you've got the correct answer. And then of course this is another solid line, and since it is greater than, we are going to be shading this one above. Okay, we're shading above. And then I'm going to take the last one, and we're going to switch this to y is less than or equal to 2/3 x plus 3. So we're going to plus 3. And we're going to go up 2 over 3, and you got some really nice intersection points right now. And we're going to go this way, and this graph we are going to shade below. So what you would do is you would take your pencil, your highlighter, whatever it is that you want to do, and we're going to go shade them. So this guy, we're shading below the purple line, and then we are going to shade above the green line. And then we are going to shade to the left of the blue line. And you can see where your final intersection area is going to be. Now notice how we have a black triangle that's stuck right in the middle. And this is what we would call a bounded feasible region, because we have, you know, it's blocked on all sides. It makes a triangle. So this is bounded. So you will have a maximum and a minimum. So what we need to do is we need to go find those intersection points of our feasible region. Okay, so just the 3 coordinates of that triangle. And we have 0, 3. We have 3, 0. And then we have this one at 3, 5. Now if your graphs are off, your intersections can be off, and then it can throw off your max and min, and you can see points just disappearing right in front of your eyes, can't you? So Then after we find those three, we substitute it back into the objective function. So this one, we have 2 times 0 plus 4 times 3, and that's going to give us 12. And then we substitute 0 into the objective function, so that's 2 times 3 plus 4 times 0, and that is going to give us 6. And then the last one, we're going to substitute 5. So 2 times 3 plus 4 times 5 is going to give us a total of 26. So we have 12, 6, and 26. The biggest number we have is 26, so that is our maximum. And the smallest number we have is 6, so that is our minimum. And that is how you do linear programming. Okay, and this one is bounded. So the next example I'm telling you right now is going to be unbounded. So what I want you to do really quick on your own, I want you to graph this on your own and then just stop and wait for further instructions. We're going to do the bounded part or the unbounded part together. Okay, so here we go. Now yours looks a little bit different. I only shaded the final answer for this because once you start shading with 4 lines on this computer, you start to get to a lot of dark areas, and this will make it easier for you to see. So when you're doing unbounded, now I want you to notice something. I do understand that there's an intersection point here. I understand there's one there. I understand there's one there, but you don't want those little green ones. You only want the red ones because the only intersection points you really care about are the ones that are created by your final feasible region. Okay? So the first thing you do is list just the 6 that you're going, or the 3 that you're going to use. The 0, 6. That you have at the intersection of the vertical line at x is greater than or equal to 0 and your green line. And then we have 1, 2. And then we have 3, 1. So those are our 3 points. Now we're going to do the exact same thing that we did in the last one. We are going to substitute all 3 of those points into our objective function. So 2 times 0 plus 3 times 6 is 18. And 2 times 1 plus 3 times 2 is going to give us 8. And 2 times 3 plus 3 times 1 is going to give us 9. So we either have a maximum of 18 or we have a minimum of 8. The question is, which one? Do we have a max? Do we have a min? And that all depends on your objective function. That it has nothing to do with the fact that this is being shaded to the quadrant 1. It has nothing to do with if we were to shade to the bottom left, bottom right. Doesn't matter where we're shading. It's all dependent on the objective function. So how do we know? We plot a test point somewhere in that shaded region. So I am going to call this my test point. So what I'm going to do is I'm going to test the coordinate 10, 10. Now you can't pick any random coordinate. It must be in your shaded feasible region. So if I substitute 10 and 10, I'm going to get 2 times 10 plus 3 times 10, which is going to give me 50. And this means we have no maximum because that's just the test point. What if we did 2020? 2020 would give us 100, and then if we kept on getting further and further out to 100, 100, it's just going to get bigger and bigger and bigger. Since it's never going to have a maximum value, we only have a minimum of 8, and we have no max. Okay? So that is unbounded. When we are unbounded, you will only have a max or a min. You will not have both. Okay? So those are the skills you need. So now let's go apply them. We're going to apply them to a word problem. So our constraints, how much can you spend, how many paperbacks, but also how many hardcovers, all of that kind of stuff. So what we need to do is we need to read this problem. We need to set everything up. So we want to make a gift basket for mom, and we want to spend $80 or less with hardcovers and paperbacks. So paperbacks. We obviously are going to have to spend or buy more than 0 or 0. We don't have to buy them. But paperbacks we have to do less than or equal to 7. Okay, because it says the basket will hold at most 7 paperbacks. But you can't buy negative books, okay? Keep that in mind. And then we have our hardcovers. So our hardcovers are going to be y has to be greater than or equal to 0, but y is going to be less than or equal to 3, because those are going to be our hardcover books. Now we have to think about how much we can spend. Well, we have $8 per paperback book, which we called X, plus $24 per hardcover, and we're going to set that less than or equal to $80 that we have to spend. Okay, so now what I'm going to need you to do really quick is I'm going to need you to go graph this and come back, and we'll see what you got. Actually, pause for just a second. I want to say one other thing. For the purpose of this problem, it'll be easier to graph this if we switch our X and Y's. Okay, so really quick, let's call this 24x plus 8y is less than or equal to 80. Now, here's a little skill when you're writing these problems and you have to graph. If you made this problem, you would have 1/3, and then you'd have to deal with a fraction. This right here will make it easier for us to graph. So this one we can switch to y is greater than or equal to 0, y is less than or equal to 7. You get what I'm doing here, I hope. So go ahead and switch these up and go graph it. So your answer should look a little bit like this. Again, the reason I had you work with this is so you didn't have to graph a fraction. When you get to assign your own variables, it'll work out just fine. Just make sure you're careful. You could have done it the other way. I was just trying to help you out. So our intersections are 0, 0, 3, 0, 0, 7, and we have 1, 7, and we have 3, 1. Those are all of the intersections. So now what we need to do is come up with our objective function. Remember, find the maximum number of books the basket can include. So that's just going to be x plus y, and that's going to be equal to the number of books. So all we have to do is use that as our objective function. And, well, obviously it's not much of a gift if we don't buy anything, so this is 0. We could do 3 hardcovers. We could do 7 paperbacks. We could do 1 hardcover and 7, because that'll still fit into our cost effectiveness and number of books. And then finally we can do 3 hardcovers, but then we'd only have enough money for 1 more paperback, so that would give us a total of 4 books. So the most amount of books we can get would be 8. All right, so there you go. That is linear programming. If you have any questions, you know where to find me. This is Longo, and I am out. See you. Bye.